Let me steer us in the direction of where we left off last time, which was starting to think a bit more than about syntax and trying to think a bit less about all of the minutiae that takes a bit of a time to acclimate to thus far in terms of semicolons and parentheses and curly braces, to start taking things a little bit to a higher conceptual level so that the problems we now start solving over the next several weeks are going to involve much more into higher level conceptual problems and a bit less in the syntactical as you get your feet wet and your hands dirty with some of the syntax from these past few weeks. So recall that last week we introduced this notion of an array. And an array in English can be described as what? Sorry? A collection of? Oh, so OK, good. A collection of items. So we saw arrays in Scratch. If you happen to use for p set 0 one of the Scratch's lists that you can drag things like oranges and bananas into, an inventory of sorts. That's kind of like what an array is. And then more technically, in the context of an actual computer, an array is simply a contiguous chunk of memory. In other words, you have a byte, then another byte, then another byte, then another byte. And if you were to draw those bytes in a picture, they would be back to back to back to back. That's what we mean by contiguous. So it's byte number 1, then 2, then 3. It doesn't mean up here, up here, up here, up here. An array is a contiguous chunk of 0 or more bytes. So what are they useful for? Well, recall we had this sort of contrived example of storing people's quiz grades in a program to compute your quiz average for some course. And recall that we could start writing that program by declaring a variable quiz1. Then we could have another variable called quiz2. But then if there were 3 quizzes in this class, quiz4. Or if there was like a weekly quiz, it'd be quiz5, quiz6, quiz7. So you'd have all of these variables declared inside of main or somewhere else in your program. And the problem with that approach, easy though it is to just copy and paste, is it just very quickly becomes unwieldy. God forbid you actually have like 30 quizzes or 50 quizzes if it's like a high school style daily pop quiz. Well, then you just have a ridiculously long list of variables being declared, and this just very quickly gets out of control. It's ugly, it's hard to maintain, it's so much easier to make a typo if you get one number mistyped somewhere in your program. So we introduced the notion of an array instead. And recall that we implemented this program by doing a little something like this. Let me go into today's source 3 Monday directory and open up an array which we saw last time. And even though there was a couple of new C tricks here, among them the notion of a constant, recall that we declared multiple floats essentially by using this syntax. Float, then the name of the variable, then we used square braces really for the first time. And what we did inside of those square braces was effectively put a number. But instead of putting a number, I put this capitalized word, quizzes. And what was the motivation for putting a capitalized word like quizzes and then using line 17's trick here to actually give that a number? What was the motivation there? Yeah. Exactly. If we want to change that value to, we only have to change it in one place. Because consider, I don't even remember what this program did exactly, but if you just skim it, you see quizzes, quizzes, you see quizzes. Down here, more quizzes. So if we didn't have this constant, this use of sharp define, we would have typed 2, then 2, then 2, then 2, which is fine. It would be just as correct. But suppose that next year we have 3 quizzes in CS50. So I have to go and update the code. I have to recompile it. But the problem is if I do something stupid, like I overlook one mention of 2 and forget to plug in 3, the whole program could very well break. So we're just asking for trouble. So the notion of a constant is all about factoring out some piece of data, whether it's a string or a char or a float or whatever, and declaring it one place so that you can more readily change it in the future. And it's also, frankly, a bit easier to read, because if you just think of this now as quizzes, or we could even rename it something like number of quizzes or something more explicit, the code just becomes a little more obvious as to what it's doing, and you wonder a little less what number 2 might happen to mean. All right, so the constant had nothing to do fundamentally with arrays. The array was introduced by way of these square braces. So notice that in line 23, we asked the user, what were your quiz scores? Then we just have this loop which apparently asks the user for their grades. How? Well, it iterates from 0 to 2. And I say 2 because quizzes, in all caps, is currently 2. So it iterates from 0 up to 2, and then it prints out quiz number something of something. And then it uses getFloat to get a value from the user. So notice this is the only other new piece of syntax from last Wednesday. If you want to store something in a particular location in that array, you again use the square brackets. So there's a bit of dichotomy here. The first time you use the square brackets, you use it to specify how big you want the array to be. But this next context here, where we again employ these square brackets, means where in that array do you want to put some value. And the distinction here can be inferred from context. Notice here we have a data type, then we have the name of a variable, then we have our square braces with a number inside, semicolon. That's it. So that's a declaration. It's just as though we had done something like float grade 1, float grade 2. But again, this very quickly devolves into way too much copy-paste. So instead, we just simplified it as such, which means henceforth, we have a grade that can be stored at bracket 0. We have another grade that can be stored at bracket 1. But what if I goof and, for instance, my loop goes so far, for instance, I make this less than or equal to, which recall was the source of a previous bug, which effectively means that on some third accidental iteration of this loop, I use bracket 2 effectively. What might happen here? Sorry? Is it going to be replaced? So what would be replaced? This literally is saying replace what is at location 2 with the return value of getFloat. But the problem is, how big is the array at this point in the story? The array is still only of size 2, because the array, like any variable, was declared first before we used it. And we specified here, because of this constant, that I have 2 grades that I'm going to put. But remember, the computer scientists start counting from 0. So the first location in that array is bracket 0. This next location is 1. This thing is ever so slightly too far over to the side. So in other words, if I actually had this array, and let me see how well this cooperates here for us. If I have an array that I've simply drawn as follows, and I've allocated space for 2 elements, I might draw this like this in memory, where this big white canvas is just the RAM I have in my computer, a gig of RAM, 2 gigs of RAM, whatever. But these 2 boxes now individually represent a float, 32 bits. So if I put one number here, like 1.0, then I put another number here, like 3.2, but then I do bracket 2, that's like putting something here. And as the picture suggests, there is nothing there. It's sort of like no man's land, because I have not asked the operating system to give me this third quiz. If I did want that third quiz, I should have had the forethought to ask the operating system for it by declaring quizzes to be not 2, but to instead equal 3. So in other words, the picture that we effectively have at hand looks like this here. This, again, is no man's land. We better not try writing values here. But again, because computer scientists count from 0, when we talk about this location in the array, that's supposed to be location 0. This is supposed to be location 1. And this doesn't even exist, because we only ask the operating system for 2 such places. So those of you with prior programming experience from other languages might know that this is not always the case with arrays or things called vectors. Rather, you can just keep adding and adding and adding things to arrays. Frankly, we had that ability in Scratch, and yet we seem to have given it up here, because with C, you are programming much more explicitly. It's only you and the computer right now, and the computer's only going to do what you tell it to do. So if you only tell it to give you 2 floats, by way of line 22 here, that's all you're going to get back from the operating system, space for 2. So increasingly, are your programs going to occasionally be buggy with regard to arrays? This is just sort of the nature of the beast, whereby all of us are fallible, and at some point you will very likely index beyond the boundary of your array. And that's just a fancy way of saying you went into bracket something, and something was just too big of a number. You went beyond the bounds of your array. But the upside now is this. The rest of this program really has nothing fundamentally to do with arrays. It's all just about some simple arithmetic for computing averages. So we have here in this for loop here, first a variable called sum that we initialize to 0. Then we iterate from 0 up to 2 again. And we add to that summation variable the ith grade, so bracket 0, then bracket 1. And then as you would do in grade school to compute the average, we simply take that sum, divide it by the total number of quizzes, and then for good measure, we call a function here called round. Now, as an aside, what is the deal with this parenthetical int on line 34? Might have come up already in section. Haven't really talked about it formally here, but what is this int in parens probably doing? Yeah, this refers to casting or type casting, which means taking one data type and converting it to another. Now, you can't do this with all data types, because sometimes it would be a bit strange. But in this case, if the return value of round is a float, because after all, I'm taking a float and dividing it by a number like 2, I'm going to get back a float. But grade school people don't really like to know that their average was 93.4, because they'll realize they were ever so close to that 95 rounding point. So we want to instead use int to round everyone to the nearest int, which in this case is going to be 94 with no point after it. So that's just a little mathematical trick. And we'll come back to this notion of a casting, because it'll have implications, if you haven't discovered already, for problem set 2. So an array, then, you can think of it's going to make me smile all day. This looks like this if you draw a picture of it. But the key is that the size is also selected by you when you request it from the operating system. All right, any questions, then, on arrays? Yeah? Good question. So question is, what happens to the null 0 in the array? Does not exist in this context. So that only exists in the context of strings, which we're about to come to in just a moment. But for an array, as in this case, all you get is what you ask the operating system for. And as an aside, lest this be unclear, I keep saying you ask the operating system, ask the operating system. So an operating system, as you probably know, is Mac OS, Windows, Linux. And when you're calling functions like getFloat, or you are declaring functions like, rather, you are declaring variables like grades, at the end of the day, you're effectively asking someone else to give you that memory. Because we, as aspiring programmers, we have no idea how to actually get physical access to memory. But someone does, the operating system. So besides presenting us with pretty icons and menus and folders and the like that you see on your desktop, whether a Mac or PC, operating systems also do the low-level mundane stuff, the highly technical stuff of managing the gigabyte or 2 gigabytes of memory that you have, managing the CPU that you have, and so forth. So when we're writing code, you're really hooking into your operating system in that sense. I'm going to have to minimize that. All right. So other questions about arrays? No? OK. So the transition naturally from arrays is actually to a topic that's a bit familiar. And we looked ever so briefly at this last time, too. This was a string example from Wednesday. And this string example was a pretty simple program. And I've actually simplified it by a couple of lines for today's purposes. All it does in line 19 is get a string from the user, stores it in a variable called s. Then in line 22 onward, it's apparently printing that string 1 character per line. But how is it doing this? Well, we're declaring a variable I, setting it equal to 0. And this is becoming old habit now. This, we hadn't seen this until Wednesday, but you can kind of infer from its name. strlen just returns what when given s? So the length of the string. So if I pass it a string, quote unquote, David, it's hopefully going to return to me the number 5 because of DAVID. So that's its purpose in life, is to take a string, whether hard-coded by you or in this case plugged in as a variable, as an argument, and it figures out what the length of that string is. So here now, we're borrowing some notation from the previous quiz example. This has nothing to do with floats, has nothing to do with quizzes, but it turns out that the little white lie we've been telling you since week 1 is that a string doesn't really exist in C. A string, at the end of the day, is really just an array. It's an array of bytes. So byte, 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 which recall is just 8 bits. So chunk of memory, chunk of memory, chunk of memory, chunk of memory. And the means by which a string is implemented is by putting the first character here, then here, then here, then here, back to back to back in the computer's memory. So if you wanted to spell out a word like hello, you would put 1 character H, then E, then L, then L, then O, 5 characters in total, somewhere in your computer's RAM. But the key detail here is that they're going to be back to back to back to back, right next to one another. So when I say S bracket I, what in English is this giving me? What does S bracket I represent in this case? Yeah. Exactly, the ith character in the string. Now, I is going to start at 0 as per my for loop here, but that's good because everything starts counting from 0. So S bracket 0 is going to represent the letter H in a word like hello. S bracket 1 is going to represent the letter like E in a word like hello, and so forth. And what we seem to be doing on each iteration of this loop is temporarily storing the ith character in a variable called C, which is just a char, and then we're printing out C so that at the end of the day, what this program does is the following. If I go into the source directory and I make string 1, and I go ahead and run string 1, and then I type a word like HELLO, enter, all it does is print this one character at a time. So there's an opportunity for refinement here. I'm kind of doing more work, even though it's more clear maybe this way, than necessary. Which line of code here can I probably throw away altogether? Yeah. Line 24. In line 24, I'm declaring a variable c. I'm storing the ith character of s in it. But then I'm using c here. So I'm using c. So I feel like I can't just throw line 24 away. Exactly. So when it comes to talking about the design of programs, notice this slight simplification of the code, which is just as readable, but realize that s is just a variable. Its data type is an array. So s bracket I is just going to instantly return to you the ith character in that string. And if you want to print it, that's fine. You just have to use %c because you're not printing a string. You're printing a character in a string. And this, too, has the effect of printing the ith character. And recall, the only difference really from last week with using printf is that whereas in the weeks past we would do something super simple like the %s placeholder, then the name of a string here. Now we're diving in a little deeper underneath the hood and saying, don't print the string, print the single character therein. So we can do something a little different here because there's one other, not bug, because this program is right, but I'm doing something stupid that I mentioned briefly on Wednesday. But thinking back, how could this program's design be improved even further? Yeah. Oh, good. So recall that we introduced a second variable called n last time, which seems to be contradicting ourselves, because my goal a second ago was just to throw away a variable as unnecessary. But recall that on Wednesday, we actually did this. I changed the for loop to actually have a comma here, then n equals sterling, and then over here I did I minus n, or I is less than n. Then I did my increment. What is the fundamental gain that I'm achieving by changing my initialization to this and my condition to this now? Exactly. I'm not recalling sterling again and again and again. Because recall how a for loop works. Even if they start to get more complicated looking, recall that the thing before the first semicolon is the initialization, which happens once. The condition, though, is in the middle. And this gets checked every time that you go through the loop. So it's kind of stupid to be asking the computer the same question again and again. What's the length of hello? What's the length of hello? What's the length of hello? Because as we'll see today and on Wednesday, this is definitely going to take time. And it's not a very good use of time, because to figure out the length of a string is actually takes a bit of effort. It's not instantaneous as it is in some languages. So by changing this to n, the price I'm paying is what? We're seeing a trade-off here. I can save time by not asking the same damn question again and again, but it's going to cost me something, which is what?
You lose a certain amount of memory.
Exactly. It's going to cost me some memory. So in this case, it costs me what? Another 32 bits, because n is just an int, as implied by the word int here. But is that OK? Frankly, that's probably OK. Because if you think about it, the longer the string is, the more time I'm going to be wasting, because sterling is going to get called again and again and again for every iteration of the loop. And these days, heck, my Mac has like 2 gigs of RAM these days, 4 gigs of RAM sometimes. I think I can afford 4 of those bytes to actually speed things up. But this is going to be a trade-off and a theme really in programming and in computer science of never really getting anything for free. If you want to improve something here, you have to pay for it in the other hand somehow. Space versus time in this case. All right, so this was all leading up toward something cryptic like this, which, as you probably figured out by now, actually says, yeah, so this is be sure to drink your Ovaltine, actually using an algorithm called ROT13, R-O-T-1-3, which just means rotate all of the letters 13 places, which means take A and then add 13 to it and go ... all the way to the 13th letter away. Do the same thing for B and for C and for D and so forth. And so if we actually convert this here, using 13, a shift of 13 places, we'll get back to what little Ralphie had, which was be sure to drink your Ovaltine. But now, for problem set 2, in the standard edition at least, you have to kind of do this enciphering yourself. And we have to somehow take in input like this and encrypt it or decrypt it. So which of these fundamentals sort of leads us to that opportunity? Well, let's take a look at this third example here. First of all, it's called ASCII. And what does ASCII refer back to? American Standard Code for Information Interchange, which is a really long way of saying what? What is ASCII? What's that? A character map. It just maps numbers to letters because the world has standardized what numbers will represent what letters so that all of us can use computers and our programs all are just compatible when it comes to printing out things on the screen. So recall that 65 happens to represent A, 97 happens to represent lowercase a, and so this simple program here, ASCII, is taking advantage of that fact that the world knows that capital A is 65, and it's just printing the mapping. So before we dive into this code, let me instead open up a terminal window. Let me go ahead and make ASCII, and then let's just run this thing just to spoil the output. And it just does this, a really big chart that just tells me all of the various codes for all of the various letters. So a super simple program, but I didn't have to hard code those 52 lines of output, 26 uppercase, 26 lowercase. Instead, I did this programmatically with a couple of loops. So notice what I did here. I iterated from I is 65 on up to 65 plus 26, because I wanted to print out 26 letters in the English alphabet. I plus on each iteration. And now notice this again. It's the recurrence of our friend typecasting, whereby you convert one data type to another. Because what do I want to do in this particular program? Well, I want to count numerically, because that's how I grew up counting, 65, 66, 67, and so forth. But I don't want to print just the numbers. I want to print the letter followed by the number. I want to print A colon number, B colon number. But I can do this with the same exact variable. So I print out %C as a placeholder for a character, %D is a placeholder for a digit or a number. Then what do I plug in for those two placeholders? I first plug in the character equivalent of I, and then I print out I itself. So notice this too just works. Just as I can cast from a float to an int in order to go from a real number to an integer, here I can go from an int to a char, which is a little weird, doesn't quite map onto the real world. But in computers, a char is just a number underneath the hood. So we're being ever so explicit here to the computer saying, printf, print out not I as 65, print it out as its numeric equivalent. And it turns out I technically don't even need this. What I was doing a moment ago is explicitly casting by specifying what data type I want to go from and to. But notice that I already have this placeholder, %C, and this other %C placeholder here. Even though this is an int, the computer realizes that a char, it's just an int underneath the hood. So if I actually recompile this and rerun the ASCII program, notice it still just works, because the computer realizes that there is this correspondence. Now, it's more important to do the explicit casting in the world of floats to ints, because there you're actually making a calculated decision. Throw away everything after the decimal point. Here, there's really nothing to throw away, because a character is just a number, and a string is just an array of characters. So when it comes time to implementing some encryption or decryption, how is it that we can actually translate something like this nonsense to be sure to drink your Ovaltine? Well, what if we know right now, let's take as assumption that the key, the number that we're rotating all of these letters by, is the number 13. So we went from the letter B all the way to O at the start of the sentence. Be sure to drink your Ovaltine, because if I do B and then I go C, D, E, F, G, H, I, J, K, L, M, N, O, that's why the encryption of B, the letter B, becomes O, because I just added 13 to it. So if I want to decrypt this, I essentially have to take O and then subtract 13 from it. Or frankly, because there's 26 letters in the alphabet, this is wonderfully symmetric, we can also just add 13, and we'll get back to the letter B. But how do you go about implementing something like this in Caesar, or really manipulating strings in general, if the letter B is what number? What's the letter B? So it's 66, right? So if the letter A is 65 and the number B is 66, so 66, all I have to do is add 13 to it, and this gives me 79. And if we go to our little cheat sheet, 79 indeed maps onto O. But there is a bit of a corner case here. What is, say, the letter Z? Well, if we do 66 plus 25 to get all the way to the end of the alphabet, we're at 91. 91 plus 13 gives me 104. And guess what? 104 does not equal an uppercase letter. Right? Let's go back to a little cheat sheet here. If I rerun this program in the appliance, notice that 104, if I go back to the terminal window, 104 is apparently the lowercase h. So we need some key trick here in order to make sure that when we start at z and we add 13 to it, we don't want to just keep forging ahead to bigger and bigger numbers. What do we really want to do? You want to wrap around. So it turns out, as you've seen probably in section now, or in the problem set spec itself, realize that there's this other operator in C that also is a percent sign, but whereas we've used percent sign here to actually get to specify a placeholder, know that, especially for problem set 2, that there's also something like this. Int x gets y percent z. Let me just present this as a very generic form of this. Percent means what in a programming language? So modulo, which is a fancy way of saying the remainder, even though there's a slight distinction with the definition there. This means divide y by z, but don't return the result of that division. Instead, return the remainder. So if y is actually 3 and z is actually 2, 3 divided by 2 is 1 with a remainder of 1. So what does x actually equal in this scenario? 1. So this is such a simple, low-level idea. It takes a little time to get your mind wrapped around it, because it's probably been a while since you even had to care about remainders and actually use them for something purposeful. But in this case, the simple fact that you can go from a big number like 3 to a relatively small number like 2 and then wrap around effectively by using the remainder to a smaller value like 1 is going to be an invaluable trick that we can use both for something like Caesar and this other thing, Visionaire, and problem set 2. But this is going to be a recurring trick throughout the semester. This simple idea of just taking the remainder in general is going to allow us to wrap around. And as we start playing more with arrays, as we start playing more with memory itself, this is going to become more and more of a powerful trick. So any questions then on ASCII or the representation of strings as arrays? And we'll take it up one notch further. Yeah? Good question. What does it mean when a variable has an asterisk in front of it? Let me postpone answering that in any detail, but that refers to a topic known as a pointer. Pointers have to do with memory, and we're actually today taking the first step toward that discussion. But for now, let me pretend that the star doesn't exist, and we'll continue calling things like we'll continue calling strings strings instead of using char star, which you've probably seen before, and I'll put on the screen in just a moment as a teaser. So we'll come back to that in way more detail than many of you will probably like. Eventually, not today. Yeah? In what context do you have to provide the sign for a character? So by default, when you don't put a plus, just positive numbers are assumed. So if you just write the number 1, it's a positive 1. If you actually want to specify the negation of a value, you literally have to do like -1 on your keyboard. But this probably isn't your question. OK. Good question. OK, so this has to do, I gather, with some kind of bug you ran into because you were converting an integer to a character, but somehow negativity got involved. And so the character just came out munged somehow. So for now, let me oversimplify a bit until we come back to this kind of topic. But for now, think of things this way. And this is an oversimplification. But in the world of an integer, you have how many bits at your disposal? So you have 32 bits. And thus far, we've talked about the total number of integers you can therefore represent is roughly 4 billion in total, because you have 32 bits, so that's 2 to the 32, so that's roughly 4 billion. But we saw a week or two ago that you don't really have a range of numbers from 0 on up to 4 billion. The range instead goes from roughly -2 billion to +2 billion. But this then begs the question, how do you represent the notion of -2 billion, let alone -1? Well, for now, we can oversimplify and just say that, you know what, we're going to use the leftmost bit of those 32 bits, and if it's a 1, it's a negative number. And if it's a 0, it's a positive number. Now, the problem with that simplified representation of negative numbers is that if you are deliberately being clever and trying to convert from a character to a number, or vice versa, there's no such thing as a negative character. In the world of ASCII, which uses only 8 bits, all 8 of those bits matter. And the leftmost bit has nothing to do with negativity. And just to be clear, when I say leftmost bits, recall that when we did our bit-related examples in the first week, recall that we drew things like 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, something like this. When I say the leftmost bit, I just literally mean the one that you write all the way over to the left. So in the world of characters, there is no notion of negativity. So that leftmost bit actually has something to do with ASCII, nothing to do with negativity. So it sounds like, and out of context, it's hard to answer exactly, but somehow your code was confusing that leftmost bit as representing a negative value when it really was part of the character in question. And again, I'm oversimplifying because computers actually do something a little fancier than just changing that leftmost bit to a 1 for a negative sign versus a 0. They instead, if you're curious to Google, use something typically called 2's complement, which is a bit more sophisticated of an approach, but the idea is ultimately the same. So in short, it had to do with the fact that you were massaging a number to a character or vice versa, but your code was not cognizant of the fact that one of those bits had significance in the numeric world. That's not the case in the character world. But it sounds like you fixed, in which case, moot now. Other questions? OK, so thus far, all of the programs we've written have taken input maybe from the user in the form of functions like getInt, getString, or if you've been reading ahead in various books or online references, you yourselves might have used functions like scanf, which frankly we use in the CS50 library. But in a week or two, we'll actually show you how the CS50 library is implemented so that we can take those training wheels off altogether. But it turns out there's another way to get input from a user. In fact, we ourselves have been using command line arguments for a couple of weeks now. Every time we have run clang or we have run make, we haven't just typed clang enter. We haven't typed make enter. What have we typically written after the word clang at our terminal Windows prompt? The file name, right? hello.c or mario.c or whatever the relevant file name is. And in that sense, what you've really done is you've influenced the behavior of clang, because certainly the people who wrote clang had no idea that little old you was going to write a program called mario.c years later. So you had to somehow influence the behavior of that program. And that program clang had to be written in such a way that it can accept input from you by the addition of words on the prompt before the user hits enter. So it turns out that for some time, we have been declaring almost all of our programs to start like this: int main void. And then we've gone ahead and started writing our code. And we might have some sharp includes at the top of the file, but almost all of our programs thus far have begun with this, even though you might have seen in section, in books, online references, that this does not, in fact, have to be void. Another legitimate form for this to take is int argc and then string argv bracket bracket. So now what is this implying? Well, it turns out that argc, which is a human convention, you could call this foo, but it would just be a lot less clear to readers. Argc just is an argument to the function called main that represents what? What does argc stand for those familiar? Yeah, number of arguments, or argument count. It's as simple as that. How many arguments were passed to this program? Now, what does that mean? Well, if on the command line I have run something like this, clang mario.c, argc, when I hit enter, is going to take on a value of, somewhat confusingly, 2. So it turns out that argc is argument count, but for historical reasons, the name of the program itself is included in that count. So argc is 2 when I wrote clang mario.c. Now, what does argv contain? Well, first of all, argv looks like a string, but not quite, because as of last Wednesday and all the more today, these square brackets denote what? That's an array. Now, there's no number in the array. And that should make sense intuitively, because the people who wrote Clang years ago, certainly they had no idea how many words people like us would type at the prompt before hitting enter. So in this case here, they have declared the function main as taking an array of arguments, 0 or more arguments. They don't know in advance how many there are, so there is deliberately no number inside of these square brackets. But the fact that the square brackets are there are telling the computer, expect an array. Now, argv is just shorthand notation for argument vector. A vector is a fancy way of saying array. An array is a fancy way of saying a list or collection. So this just means that if you write main like this, instead of like how we've been doing it for the past couple of weeks, your program now has the power to accept command line arguments, so that no longer do you have to write Mario and then hit enter, then type in a number for how many blocks high you want the pyramid to be, then hit enter again. We don't even need to use getString anymore, or getInt, or getFloat, or for that matter. We can just expect the user to type those words at the prompt itself, just like the authors of Clang decided, you know what, it would be a really annoying program if to compile your code, you first typed Clang, hit enter. Then we said to the user, please type the name of the file you want to compile. Then we type in mario.c and hit enter. But that's exactly what we've been doing to our users the past couple of weeks. We use getString, and we wait until the program's running to prompt them for input. That no longer needs to be the case. So in this example here, we now have string argv, and this too is an oversimplification, training wheels that will very soon come off. This is the more proper way of writing this alternative declaration of main, because it turns out that what we keep calling string actually has a star, an asterisk in its actual definition, but this just looks complicated, it's confusing at first, so we simplify by just creating a synonym of sorts in the CS50 library that maps char star to this more user-friendly word, string. So let's actually try this then. Let me go ahead and open up gedit here. Let me go ahead and open argv of 1. And this program apparently prints the arguments, but in English terms, by looking at this code, what does this do more specifically? If I type in the command a.out foo space bar, what gets printed in my black and white window? A.out space foo space bar enter. Go ahead. Yeah. Good. So a.out, new line, foo, new line, bar, new line. Well, why is this? We can certainly confirm in just a moment. So this is kind of a fluffy line of code. It just prints a new line just to make things prettier on the screen. This is a loop that's iterating from 0 on up to argc. And this is incrementing on each iteration, ++. So this is now saying print a string, as implied by this %s. argv bracket I is pretty much the same idea from the previous example. We used to call the variable s. Now it's called arbitrarily argv. This means print the ith argument that was typed at the command line. And then after this whole thing is done, just for good measure, print another new line. So let's see this. Let me open up the terminal window. Let me compile argv of 1. And now let me run argv of 1, enter. OK, let's run foo bar. Interesting. Baz. And if you've ever wondered why I type this, this is just also a stupid computer science convention. The world often needs just verbal placeholders for words. So if you want to talk about some generic string, computer scientists just tend to say foo when they need a random word. Then they say bar if they need a second random word. Then they say baz if they need a third word. Then they say quux if they need a fourth word. And then there's a huge religious debate online as to what comes after quux. So you can Google that to figure out what the other arbitrary words should be. But these have no meaning whatsoever. Though foo bar, if you Google that does have meaning, so which is part of the etymology here. So all this is doing then is printing one of these strings per line. So if I instead, though, wanted to get a little fancier, suppose that I didn't want to print each string per line. I wanted to print each character from each string per line. How could I instead do that? What do I need to change about this program if I want to print not each word, but I want to print each word letter by letter by letter, then the next word, letter by letter by letter? How do we combine these ideas thus far? Yeah? All right, so we somewhere need a %c. Good, because I don't want to print whole strings. I want to print characters. What else? Interesting. So we need sort of a second dimension here now, because think of strings, argv is an array, but it's an array of strings. But as of like 15 minutes ago, what's a string? It's an array of characters. So really, argv is an array of characters, an array of arrays of characters. So it turns out that we can use just more square bracket notation. So let's do this. In the top of this loop on line 19, I'm going to iterate from I up to argc. But then I'm going to do this. I can't use I now. I need another variable because I want to iterate over the words, but then also over the letters in the word. So I sort of have like a vertical axis and a horizontal axis, sort of conceptually. So int j gets 0. Then I'm going to do j as long as j is less than, and I'll clean this up in a bit. How do I iterate over the letters in a string? We did this a moment ago. Strlen of argv bracket I. Good. And again, I'm making a little inefficiency here by not creating n or whatever, but we'll come back to that. So now j++. Now I have to indent further here. What do I now want to print on each iteration? So bracket I will give me the word. Bracket I, bracket j, sort of like a matrix. Those of you with mathy backgrounds, we're sort of indexing even deeper into this matrix, or this array of arrays, this two-dimensional structure. So now let's see what happens here. Let me open up my bigger terminal window. Let me rerun make of argv of 1. And I've screwed up here, which is a good lesson, because I too forgot to do this, implicitly declaring C library function strlen with type unsigned. I don't even know what the rest of that means, but I have seen this before, implicitly declaring. Whenever we see this error, what does this usually signify? I forgot a library up top. But wait a minute. Usually I've screwed up because I forgot the CS50 library, but that's there. Usually I've screwed up because I've forgotten standard I/O. And frankly, I don't even need this. We're not using getString today. So what am I missing? So there's another library that now we need to use occasionally called string.h. And this is just yet another library that has more functions that aren't in standard I/O. So let's go back to my big terminal window. OK, now, damn it, I guess I was wrong. I was using the CS50 library. So we can fix this in either of two ways. We can take the training wheels off right now and just do this. Or let's kind of keep that simplification just for now, paste this back in, solve that problem, and now go back to the terminal window. So to be clear, in the CS50 library is not just functions. It's also the keyword string, which is why that error just happened. So here we go. I fixed the library. I fixed I fixed both of the library issues. Enter. Good. argv of 1, foo bar, enter. Excellent. So now we have each letter of each word printed one per line, which does not make for a very interesting program. But notice now we have the capability of not only iterating over words, but also over individual letters in words, which sounds awfully familiar to even the simplest of applications like scrambling letters in a string like this. Let's go ahead and take our 5-minute break here. And when we come back, we'll start talking about the efficiency with which we can do these things better. All right, so we are back. And thanks to one of our TFs who plays a lot of bananagrams, we actually have a whole bunch of chars with us here today, physically incarnated with these little plastic pieces. And let me propose that this blank white slate here represents the RAM in my computer, laptop, desktop, whatever. And there looks like a lot of it, because if we start chopping up this RAM into small bite-sized pieces, let's arbitrarily say that something that size and that blurry represents, there we go, and let's zoom out a little bit here. So let's say something that size represents a single byte. So we can indeed fit a whole bunch of bytes or characters inside of this memory, as suggested by the relative size here. So suppose now that the goal is to allocate memory for a string. How does this actually work? Well, in the programs we've been writing, we've usually been using getString. But now clearly there's this other channel via which we can get user input in argv via command line arguments. But what's really going on underneath the hood? Well, it turns out if we call, let's scroll back to getString, the function getString in the CS50 library, the user is prompted for a string. The user types in some word. Let's call it hello. And we've been saying for the past couple of weeks that the return value of getString is, in fact, a string, like the word hello. But what is getString really doing? Well, as the user types in hello, enter, getString is figuring out, okay, how many characters is this? This is HELLO, so it needs to allocate. It needs to ask the operating system, Linux in this case, for at least 5 bytes to store hello. And what it then proceeds to do, once it gets back those 5 bytes from the operating system, is to lay out HELLO back to back to back to back. And so what's really returned from getString is a chunk of data that looks like this. But this is a bit inaccurate, because it turns out that it's not as simple as just storing HELLO in the computer's memory. Because suppose that my program that I'm writing in C then calls getString again, and the next word the user types in is BYE, buy. Well, I need to fit that word buy somewhere in memory. I can't clobber hello. For instance, I don't want the computer to just start overwriting like this the original word, because I might still be using the word hello in a variable somewhere else in my program. So BYE has to end up somewhere else in memory. But the convention typically is that the next string you allocate probably, but not always, is going to end up at the next available memory location. And if I haven't asked the operating system for any memory since the last time I called getString, odds are the word buy is going to end up right after the word hello in memory. But at this point, you can perhaps see where a potential problem arises. Because the next chunks of memory, the next bytes that were just free, clean white slate in the computer's memory were right next to hello, it feels like the first string I asked for might suddenly now change, because I've essentially changed it to hello bye, instead of somehow demarking the start of buy and the end of hello. So it turns out that what's really going on underneath the hood, which you might have glimpsed in online references or section or books or not at all just yet, is that there is actually a deliberate demarcation between words that in a computer's memory. And in fact, in this case here, rather than just put buy right next to hello, instead, the computer puts a special character, the special null character, so to speak, which is represented with a marker with \0. So long story short, recall that characters are represented in ASCII. ASCII is just a mapping between numbers and letters. And most of those letters start at roughly 65 for capital A. But it turns out you can certainly represent the number 0 as an integer or in binary. And it turns out the world decided long, long ago, you know what? Let's reserve number 0 as not representing any characters on the keyboard, no letters, no numbers, no punctuation. 0 is special. It's going to be the special null character, and we're going to write it as \0. The difference being, if we just wrote 0, 0 is a character. Recall that there are ASCII codes for 0, for 1, for 2, for 3, because the character 0 is different from the number 0. And you can see that if you look back from like week 1, when we first talked about ASCII, 0 and 1 and 2 and 3, all the way up to 9, had their own ASCII codes. They are not, coincidentally, 0 through 9. They're very different. So 0 just means I am special. And the \0 means I'm not literally the 0 character, I'm this special value, the null character. So I actually need another one of these, since I can't make the same mistake twice. So after the word buy, we're also going to need another one of these null characters. So let me grab my pen here. Let me quickly draw another \0, so that after I have asked the operating system for 2 strings via getString followed by another call to getString, this is what's actually in memory. So when I get back a string, I'm really getting back that. And when I get the next string, I'm really getting back that. So this begs the question, strlang, first of all, what should it return? When I call strlang on the string s, and s was the word hello that the user typed in, what did we obviously say the length of hello was a few minutes ago? It's 5, right? HELLO. And that's indeed how strlang works. It returns what a normal human being would expect the length of a string to be. But in reality, how big is the array of characters that's storing hello? It's actually 6. So strlang does not mention that fact to you, but underneath the hood, the computer is indeed using 6 bytes to store a 5-letter word. And this is true no matter how long the word is. There's always going to be a special null terminating character at the end of the string to demark its total length. So then if you are now the person implementing strlang 20, 30 years ago, how do you go about implementing strlang itself? We take for granted that it exists, just like we take for granted that printf exists. But if hello is the word in question, And what I have in memory is something that looks like this. If you had to re-implement Sterling because you were asked to, or because, frankly, you didn't know Sterling existed, you had to roll this one on your own, how could you implement Sterling when given something that looks like this? Well, now that we know a string is an array, we can iterate over each of the individual characters using something like, let's try to do this on the fly. Let me go into the appliance. Let me create a new file, sterling.c. Let me go ahead now and do include standardIO.h so that we have access to printf. Let me do int main void. Oh, I'll just do this on my own for now then. Thank you. This is what I'm doing. All right. So before I turned on the screen, I typed all of that. And now what I'm going to do is the following. Printf, give me a string. That's just fluffy instructions. Then let me do string s get string. I already need to make a change now. I'm using the CS50 library suddenly. So let me go ahead and type in cs50.h. And now let's do this. Printf, the length is %d, sterling of s. And I'm not done yet. What else do I have to add to this program? String.h. So for now, we're using Sterling. So let's make sure the compiler knows where that is. So a little sanity check. I'm getting a string in line 8, and in line 9, I'm printing out its length with %d. So let's go ahead and open this up. We have make Sterling. Compiles OK. Sterling. Let me zoom in. Enter. Hello. Enter. The length is 5. OK, so Sterling seems to work, but the world knew that. So let's now implement Sterling ourselves as follows. Let me take this library away. We no longer have access to string.h because I didn't even know it existed. But that's OK, because I can implement Sterling myself and have it take a string called input. And now I need to figure out the length of this string. So how can I do this? Well, what if I do, let's see, how to do this. What do you want to do? OK. So we can do this in a bunch of ways. Let me try to take this approach. Let me give myself an int variable I. So I starts at 0. And let me say this. While input bracket I is not equal to what? \0. So it turns out, as with the case with all chars, when writing them literally in a program, you have to use single quotes, not double quotes. So if I were writing the letter A, I would do that. The letter B, I would do that. This, by contrast, would be a string, not an individual character. So I want \0 literally. What do I want to do in this loop? Well, actually, I need another variable. So int length gets 0. Even if you weren't sure why we started the way we did, now that we're going down this road, what do I want to do in line 9? Length plus plus, and then down here in line 10, return length. So how is Sterling implemented? It's actually implemented probably like this. Maybe the person used a for loop, maybe a do while loop, who knows? We'd really have to look underneath the hood at the actual source code in some file called string.c probably. But here, let's think about what I'm doing. I'm declaring a variable called I, setting it equal to 0. I'm then declaring another variable called length, setting it equal to 0. Then I'm saying while the ith character in input is not equal to the special null character, \0, increment the length. But as soon as the ith character is this special character, what happens to the loop? It short circuits, it stops, which means we then instantly return length. So if I didn't mess up, let's go ahead and go back to my terminal window. Let me recompile, and I did screw up. Incompatible redeclaration of library function Sterling. So I was trying to get too clever for my own good here. The compiler actually knows that there's a function called Sterling, even though we haven't included the library. So that's fine, whatever. We're just going to cooperate then. Let's rename this length. Let me change the use of it to length here, and this will make Clang happier. All right, so that's because, as an aside, because some of these functions are so darn common, Sterling, Printf, they actually have sort of special status. And so Clang just knows a little something special about them. That's not always the case with most functions. So that's why we got yelled at. Let me try again. Thankfully, it worked that time. So now let me run my own Sterling program. Give me a string, hello, enter. And I have screwed up. Why? Exactly. So I have myself here a very nice looking infinite loop. because even though I'm incrementing length on each iteration, what am I clearly not doing? I'm not incrementing I. OK, oh, easy fix. Yes? OK, no, now we would run afoul of some other common mistake, right, where I need brackets. And frankly, this code's starting to look ugly, so we'll take a stab at cleaning this up in a moment. But now I'm incrementing both length and I. Frankly, I already see an opportunity for improvement here, but we'll come back to that. So now let's just make sure we're at least making progress. This has happened to a few of you, and I neglected to mention this in advance. When you do have the misfortune of a scenario like this, how do you fix this short of restarting the appliance or your computer or closing the window? It's actually easy. Control-C will send this little caret symbol C, and that just terminates most programs. If you have a really bad infinite loop that's printing stuff infinitely many times, sometimes you might have to hit Control-C like 1,000 times to make it actually hear it. But so just realize now, because I'm not printing anything, that was quite easy. And technically once suffices, but I get impatient and I usually hit it that many times. So strlang, give me a string. Hello? Is it going to work this time? OK, another common mistake, have to recompile. So now, that was deliberate, that one. All right, so strlang, Hello, enter. Excellent. So we now have a strlang the 5. So we have literally re-implemented that wheel. So now let's clean this up, because this does not make me impressed with the design of my code. What can we clearly eliminate in this program to clean this up? Yeah, literally, we're treating I and length identically. So why don't we just get smart and say let's just call it length to begin with, initialize it to 0, because by default the string has no length until we figure out what it is. Now we do this, and now this is a pretty elegant program. One variable, I cleaned it up, tightened it up. So now let's go back to my terminal window. Let's go ahead and run this, make strlang, looks good. Run strlang again, enter, give me a string, hello. Enter, and it seems to be working as 5. Now, to be clear, if I had not written, for instance, hello in one string and then bye in another, we can certainly have multiple words. If the expression I actually wanted to type was not hello, but for instance, hello world, notice that what we would not have is this situation here. Right? That would suggest that that's 2 strings. You certainly can have space bar characters. So if we actually typed in a longer phrase like hello world, what we would really have in memory looks a little something like that there. All right. Any questions then about the representation here of strings? No? All right. So I said earlier that calling strlang again and again, deliberately like that, probably isn't the best idea, because you're going to be doing a whole lot of work again and again and again. Indeed, what kind of work is necessary for figuring out the length of a string, apparently? Well, you have to start at the beginning and then look until you finally see that special character, at which point, now I know the length. So earlier, when we had strlang being called again and again and again, the reason I proposed that was kind of stupid is because, again, that string looks like that. It's not going to change every time you iterate through some loop, so you're doing unnecessary work. Now, at the same time, you should know as an aside that compilers like Clang these days have been developed over many years, and compiler writers, the programmers, are pretty smart. And so it turns out that Clang and other compilers can actually figure out that, OK, yes, you wrote strlang in your condition, which technically means that we would call it again and again and again. But smart compilers can actually optimize those kinds of poor user decisions out of your code to redress things. So do just realize that sometimes the compiler is smarter than us, and we'll kind of hide our own mistakes. But certainly when it comes to problem sets and the like, do be thinking about those fundamentally erroneous design decisions potentially, for the simple reason that we'd be doing way more work than we actually have to do. But how much more work? Well, in the case of hello world, let's start to generalize the size of this problem. What's the length of the problem, or the size of the problem, when the word the user typed in is hello? Well, it's apparently 5, maybe 6, plus or minus 1, whatever. It's so close, we'll just call it 5. So what's the size of the problem here when trying to figure out the length of hello? It's 1, 2, 3, 4, 5, and maybe 6 for the last character. But let's generalize that as n. So n, just the variable n, is what computer scientists would typically use to describe the size of a problem. And the problem at hand is, how long is hello? How much time does strlength take? Well, it takes on the order of n steps, where each step means look at a character, look at a character, look at a character. And we had this discussion a while back, the number of operations something takes. In the very first day of class, we had everyone awkwardly stand up, and then everyone started pairing off with each other in order to actually count, ideally, how many people were in the room. And we also did another thing whereby if I instead did it the old school way of just starting 1, 2, 3, 4, 5, 6, and so forth, that too, the size of that problem was of size n. There were n people in the room. But I could speed that up, right? Grade school style, I could start counting in 2s, 2, 4, 6, 8, 10, 12, and that feels so much faster. And indeed it is. It's literally twice as fast. But again, if another 400 people walked into this room all at once, those algorithms would take another 400 or maybe 200 steps. But by contrast, if we really get smart and we instead have all of you count yourselves, recall how that algorithm worked. You all stood up. Let me fast forward to this. You all stood up, you paired off, then half of you sat down, half of you sat down, half of you sat down. And on each iteration of this loop from week 0, we halved the problem at hand. N went to n over 2, then n over 4, then n over 8. And the implication of that is that if another 400 people walk into the room, no big deal. It will take us one more round, not 400 more rounds, not 200 more rounds. And so the story we told a while back had to do a little something with this. This red line here is linear. It's straight, and it's labeled as n because as the size of a problem grows, if your algorithm or program with which you're solving it takes n steps, we can plot it as a straight line, where it takes more time the bigger the size of the problem. And the twosies approach, counting 2, 4, 6, 8, still a straight line, just a little better. It takes a little less time. So the yellow line is below the red line, point for point. But even better was this holy grail of what we called logarithmic time, where even if, again, we double the number of people in the room, we double the size of that phone book from the first day of class, no big deal. Takes one more page tear, takes one more sitting down in order to solve a problem that's twice as big. And so the conversation we now get to start having is how do we actually solve problems efficiently? If we consider the simplest of problems like this, suppose we have 8 doors behind which are some numbers. And each of these numbers is not sorted in any way. They're just random integers behind these doors. And we ask the question, how do you go about finding the number, who knows, 7 behind these doors? Well, what would you, a human, do in order to find me the number 7? If, again, each of these are doors, and to see a value, you have to open a door. What would your algorithm be, perhaps? So start with the left and open the door, open the door, open the door. And in the worst case, how long is it going to take us to find the number 7? And again, they're not sorted, so it's not as easy as, well, I'm going to open the 7th door. It could take us maximally 8 steps. In the worst case, 7 is randomly at the very end of the line of doors, so we might have to try all n doors. So again, here we seem to have a linear algorithm. Well, in fact, we did this just a couple of years ago. One of your predecessors was challenged with precisely this, where we didn't have a digital version. We instead had a blackboard with some pieces of paper on them. And what I thought I'd do is take a quick look back at how this went. One of the best and perhaps most awkward opportunities on stage to have a demonstration right here on Sanders. And we had 2 rows of numbers. We're only going to look at what happens here with Sean for the very top of these rows, unless no one ever again volunteer in CS50. We had Sean's blessing to keep this on camera, so he knows that hundreds of people have been watching this now for years. But Sean did an amazing job, or did he, at actually finding us a particular number. So let's see how he solved this algorithm so that we'll resume this conversation before long of how
OK, so your task here, Sean,
find things efficiently.
Is the following. I have hidden behind these doors the number 7, but tucked away in some of these doors as well are other non-negative numbers. And your goal is to think of this top row of numbers as just an array, or just a sequence of pieces of paper with numbers behind them. And your goal is, only using the top array here, find me the number 7. And we are then going to critique how you go about doing it. All right. Find us the number 7, please. No. 5, 19, 13. It's not a trick question. 1. At this point, your score is not very good, so you might as well keep going. 3. Go on. Frankly, I can't help but wonder what you're even thinking about. So only the top row. So you got 3 left. So find me 7. 17.
So on Wednesday, we will dive into this and more sophisticated algorithms for finding things. For now, we'll leave you with Sean and see you on Wednesday.